Next topic that we are going to cover in this class is powder metallurgy. Um, Powder metallurgy is a process that can be used to shape um, metal into the shape that we want. It's one of the particulate processing technique. Okay, so basically, powder metallurgy is a process that we use powder of metal to produce the shape that we want. So it is basically we are making the powder and we're mixing the powder together and compacting it into the shape that we want. So the powder metallurgy process involves mixing elemental or alloy powder, right? So first of all, we have to produce the powder, right? So we have a process that is called atomization to produce a powder. So the powder can be either elemental powder, so powder of different elements, for example, powder of zinc, powder of copper, powder of iron, uh, powder of chromium, etc. Or it can be alloy powder, like powder of brass or powder of stainless steel, right? Um, and then we mix them together, and then we compact them into a die. All right, so we have the powder, we mix them, we compact them using a hydraulic press usually into the shape that we want, and then we put the compact product in an oven or a furnace in a process called sintering. Right, this sintering process is heating the shape that we want and make it into a more solid piece. It is a cost-effective technique to produce simple or complex part in manufacturing, uh, and we can produce from like a few hundred to several thousand parts per hour. Right, so it is quite flexible. You can produce like small number of parts or large number of parts, and um, because we are using powder that is either elemental powder like powders of zinc, copper, iron, chromium, etc., or we can use either powder of alloys as well. So because of that, we can usually produce some sort of exotic alloys with different properties that we cannot do with other technique. Like for example, if some alloys when you mix them together, some metals when you mix them together, they don't melt very well. Right? They don't melt very well, and that will make it difficult to cast into the shape and or to cast into the net shape or near net shape or cast into a primary shape and then do machining process. But you can do that by mixing the powder together and then heat it up so that it will bind into one piece. Right? Uh, for example, um, if you want to produce a part made from brass, you can either use brass powder or you can mix copper powder and zinc powder together in the proportion that you want. Mix them together in the blending process, right? So first of all, you produce a metal powder in a process called atomization, which we will look at shortly, right? So you produce the metal powder and then you will mix them together in the proportion that you want, either mixing the pure elemental metals, copper powder and zinc powder to produce brass, or you can produce like brass powder and use that brass powder straight away, right? After blending, you can do next step is compaction. The compaction is the step that you produce like the shape that you want. So it will produce net shape. It will produce near net shape or net shape products. After compaction, which you're using pressing technique like isostatic pressing or rolling or extrusion, injection molding, etc. It can either be hot compaction or cold compaction. Um, after that, after compaction, you need a sintering process. Right? Sintering process is basically heating it up until the powder bind together to form like one big piece. We will look into detail in a sec. Right? After that, we will get the near net shape product, which we will do the secondary or finishing operation like machining, like drilling holes, etc. Okay, so and then we will get the product that we want, and then we can use it in the application we want. Okay, the first step is the production of metal powder. So the metal powder can be produced in many techniques. One of the most widely used techniques to produce metal powder is called atomization. So in this technique, the molten metal is broken up into small droplets by spraying it on the stream of inner gas or air jets or water jets, and the molten metal will rapidly solidify. Right. So up here you have molten metal. It can be molten alloys like brass, like stainless steel, etc. Or it can be pure metal like copper, zinc, iron, chromium, etc. You have uh, molten metal here, and then you you spray it down here, right? So you have uh, at the nozzle here you have either uh, gas pump or water pump. You pump in like high pressure gas or high pressure water, and you open a gate for the metal to drop down here, the molten metal to drop down here, and it will atomize. So atomization actually means to make it into small droplets, right? So when the droplets of molten metals uh, or when the molten metal becomes droplets, they will have large surface area to volume ratio, right? So because you have small volume and you have high surface, it cools down really quickly, so it will solidify straight away, right? So it will solidify rapidly or straight away. Then you would get powder, right? So you collect powder at the bottom of the gas atomization process, yeah. This is the gas atomization process, or you can use water jets. You spray water jets onto the molten, like the stream of molten metal. You get water atomized powder. So usually the shape of the powders look different between the gas atomized and water atomized. Right? Okay. Okay. Other methods of producing powder, including uh, mechanical combustion, electrolysis, and chemical process. Mechanical combustion is basically you are using a sort of a blender or a grinder, like hammer milling, right? So you put in a big lump of metal in there, and you have hammer mill. So you have like big hammer attached to this roller here, and it will just keep rotating and hitting on that piece of metal until it breaks down into smaller pieces. And when it is small enough to pass through the sieve, the powder will just like go through the sieve. If it's not small enough, it will just keep getting beaten by the hammers until it is small enough. And you can see that the powders from this technique are sort of like flat this shape because it has been beaten up, right? It's not spherical or like sort of irregular shape, like but three-dimensional, like atomization, but it's more like flat plate-like powder, right? or you can have electrolysis process, like for example in this process when you have electrolysis of copper, right? So you get powder of copper. Okay, so because of the different techniques in producing powder, you have different different powder properties from different techniques. You have different sizes, different size distribution, different shape, right? Uh, and because of this, the powder will have different flow rate, different density, and different compressibility. Okay. Okay. So that's atomization, right? So we produce powder from atomization or reduction, combination, etc. Electrolytic deposition. All these techniques are used to produce metal powder. The next step is blending, right? So we are blending the powder in the proportion that we want to produce a mechanical properties that we want. Okay, after blending is compaction. Okay, so compaction is a process that is converting loose powders into green compacts of accurate shape and size using dye, right? So you put the powder inside the dye, right, and then the punch will move down and compact in the shape that you want. So in this case, an example would be making a disc shape piece of material, right? And this product after compaction is called a green compact, or a green product. Okay, so it has the correct shape already, but it still doesn't have the strength, right? It doesn't have the strength yet because in this stage, well, initially when you put in the powder, the particles are just like separating, right? After compaction, the powders get closer, closer, closer. There might be some deformation of the powder, right? Okay, and you get a green compact product. It looks it looks like the product that you want, but it doesn't have the strength yet. For example, you can use your hand to just sort of like press on it, and it will just disintegrate in your hand, right? So this is the sort of strength that you have. So basically, no strength at all, right? But it has high enough strength to hold the shape, but doesn't have enough strength to withstand any external load at all, right? So that's the green compact. And the green density after compaction depends on the mixing particle ratio, compacting pressure, and pressure distribution. So the the density of these compact uh, depending on the compaction pressure, right? So you can see that if you increase the compaction pressure, the density will increase, right? Because the space between the particles will get smaller and smaller as you increase the compaction pressure. Okay, so even at high compaction pressure, like when you get homogeneous deformation, like in this picture here and this picture here, the particles are sort of deformed a little bit. They still don't have any strength to withstand external loading, right? It will have it will have enough strength to hold the shape. So if you compact it into any of these shapes, it will stay in these shapes. But if you hold it up and you use your finger to just rub on it, it will just disintegrate. Okay, so it doesn't have any strength yet. Okay, so um, okay, another factor that affecting the density is the mixing particle ratio, and For example, if you have just small particles or just large particles, you can see that the packing density will be quite low, right? Right? Like if you have just small particle, you have this like this much packing density, and if you have just large particle, you will have this much packing density. But if you're mixing the large particles and the small particles, you get much better packing density. In fact, you will get maximum packing density when you have like mainly large particles and you have a little bit of small particles to fill in the gap between the large particles. In fact, this is the same concept as in concrete. In concrete, we have aggregates, which is made from crushed rocks, right? And also we have sand as fine aggregates. So basically, the strength the strength and the density of concrete comes from the the main aggregate, which is the crushed rocks. But if you have just like big chunks of rock, you have a lot of holes between those pieces of rocks. So you need sand, which is a fine aggregate, to go in and fill in the hole between the big chunks of rocks as well. So it is the same concept. So if you mix two types of particle with different sizes, you would get higher density. Okay, so but why do we need higher density? Because remember when we are manufacturing it using other technique, we have 100% we have 100% density. In other words, we don't have any holes. Like from casting or machining, we don't have any holes in there. But in this technique, we have holes inside our material, right? And when you have holes, the strength will go down. That's why we want higher density as possible to increase the strength of the workpiece. Okay, and another way to increase the strength, remember I told you that after compaction, it has it has enough strength to hold the shape, but doesn't have enough strength to withstand any external load, right? The next step will give it that external strength. Like the next step will give it the strength to withstand external loading. That step is called sintering. Sintering is a step when you heat the material to below the melting point, right? So it is at a high temperature. You heat it to a high temperature, but below the melting point of that material. But that material is high enough to allow bonding or fusion between each individual particles under protective atmosphere. Right? So you can see that these pictures are from like the same piece, right? But different magnification, higher magnification down here, right? So there, this picture, these pictures represent sintering at a temperature for a longer time. Right? So you start off during the sintering process. You can see there are a lot of holes. There are a lot of empty spaces, right? And if you sinter at longer and longer time, you can see that the particles start to fuse. The particles start to fuse and bond together, right, into like bigger and bigger particles, and you have small holes, well, less empty space basically. So if you look at this picture here, and you look at this picture here, it is from the same place. You can see this hole here, right? It developed into this hole, into this hole, into this hole. So it is the same place in the material, and you can see that in this picture you have a lot more darker area than this picture, right? That means you have less hole in this picture, less pores, less voids in this picture. That means the material becomes more solid. You get higher density, and because of the fusing of each individual particles into like bigger and bigger grains, you get higher strength. So after sintering, uh, if you choose the correct sintering temperature and sintering time, the sinter density will increase and the porosity will decrease. Okay, so you increase density, you will decrease porosity or the holes inside, and you will increase the strength significantly. Okay, so that's the basic uh, powder metallurgy. You mix the powder together, you compact it, you sinter it, you get your final product. And then some engineers thought that okay, for polymers we always use injection molding to produce different shapes of polymer product, and it's really fast. It's really cost effective to do that for polymers. Why don't we do that with metals? So they try to invent a method which is called metal injection molding by adapting the technique that we use to produce like polymer products, right? So we are using injection molding machine to produce like the product. So typical product that's typical products that are made from polymers that you see in everyday life, I would say about 80 or 90% are made from injection molding process. Okay, so it is used a lot. It is really widely used. So the engineers thought that it could be adapted to produce metal parts as well. So basically, you are combining metal powder with binders to produce like feedstock, right? So you're mixing the metal powder and binder together to produce a feedstock. Um, right? So you're mixing to produce a feedstock, and then you feed the feedstock inside the injection molding machine, and then you use the injection molding technique. So basically, you have a mold that can be open or closed. You are injecting the metal powder and the binder into the mold, leave it to cool down, and then take it out. The binder are usually made from polymer, so in the injector, the polymer sort of melts, and it will carry the powder with it and fill in the mold, right? So you get a raw product, which is mainly the powder with a little bit of polymer that binding that the polymer is binding the metal powder together, and then you clean it, and then you remove the binder or debinding, right? You clean it and then you remove the binder in a process called debinding. So basically, you burn it off or use some sort of solvent to melt the polymer away. You are left with the metal powder that are sort of like held together loosely, just like green compact. Okay, and then you put it in the furnace for the sintering process, just like in the compaction technique, right? After uh, after debinding, you get the green product, right? Green body. You put it in the sintering process, you get the final product. It is a lot faster than compaction, and the shape can be more complex as well, right? Compaction can usually have some simple, relatively simple shape, but this technique can produce more complex geometries. Okay, so next technique or other methods of producing um, powder metallurgy product. We have cold isostatic pressing and hot isostatic pressing. So these two techniques are very similar in a way that they are using pressure to compress on the workpiece, right? And the pressure is the same in all directions because we are using flexible mold, and we are using like um, gas to okay, so gas or we're using liquid like gas or water, right? So that's where isostatic pressing come from, right? So you're applying pressure in all direction, so that is isostatic pressure, right? And it can be done at low temperature and high temperature, right? If it's performed at low temperature, it's called cold isostatic pressing. If it is done at high temperature, it's called hot isostatic pressing. So basically, the powders are compacted in elastomeric molds in either a wet or dry bag process, right? So for cold isostatic pressing, the powder is put in elastomeric mold. So basically means flexible mold made of rubber or polymer that is like quite flexible, and it can be a wet bag or dry bag process. So a wet bag means you are using water as the main pressure generator. A dry bag is when you're using the gas as the pressure generator. Okay, it is used mainly to produce parts where the high initial cost of a pressing dies cannot be justified. So that means you are producing just a few parts. You are not mass producing it just yet. You're producing it like a, a, a prototype or prototype runs, right? Or when you want to produce a large and complex compacts are needed. So you are producing a mold that is made from rubber, which is a lot cheaper than pressing mold made from tool steel, right? And you are in, you are doing a test run using this process. Um, but for hot isostatic pressing, the powders are compacted in steel can. So the mold are made from steel, not like elastomer, like in this case, because we are going to apply pressure and high temperature at the same time. So the elastomeric mold, the flexible mold, might not be suitable at high temperature. So we are using like steel can. We are putting the powder in the steel can container, and then we are putting all the steel can in this pressure chamber. We are utilizing the elevated temperature or high temperature and isostatic gas pressure to sinter the workpiece, to eliminate the porosity, to eliminate the pores or the empty space inside, to increase the density, and that will increase the mechanical properties uh, of the material, and will also increase the workability as well. Okay. Uh, Application for powder metallurgy include components that offer cost-effective alternatives to machine components, casting or forging. So small industrial parts that is like difficult to cast or difficult to forge, you can use powder metallurgy to produce like small gears, like one of those like really expensive watch you uh, that have small like mechanical movement inside. The gears are made from powder metallurgy process because it is easier and it is more cost effective than using like machining process. Okay. Um, the the um, powder metallurgy technique is used when the components require composition of mixed alloys or unique alloys or composite material. Like for example, in this cutting tool bits, right? The cutting tool bits is made from cermat. Cermat is a type of composite material that consists of ceramic and metal. Okay, cermat. Cermat is short for ceramic and metal. So in previous chapter when we were talking about the cutting tool. Uh, one of the cutting tool that one of the cutting insert that we use is cemented carbide, right? Well, we might be using tungsten carbide, and we have cobalt as the binder. So that cutting bit is made using powder metallurgy. So basically, we are mixing tungsten carbide powder with cobalt powder, and then we are sintering it until the cobalt bind together and form into this one piece and hold the tungsten carbide in piece, right? So we want the hardness property of the tungsten carbide. We are using cobalt more or less like a glue to bind all the tungsten carbide together, right? So the components are have unique property, right? So and we can use it to mix like different exotic alloys or composite material. So say let's think about a way that we can make this like cermet instead of using powder metallurgy. So instead of using powder metallurgy, we have to melt cobalt and then we have to mix in the powder. And because the powder is so small, it is really difficult to mix in the molten metal. So it is easier to mix the powder of cobalt and powder of tungsten carbide together. Okay, and sometimes this technique is used to produce a component that is really difficult to produce using other techniques, such as uh, um, material with high melting point, material with high hardness. So it is difficult to cast, it is difficult to machine because of the high hardness, etc. So we are using this powder metallurgy to produce like a near net shape uh, component. Like in this case, we have iron nickel based super alloy turbine blades. It is made using powder metallurgy because this is a very uh, high temperature resistant material, so it is difficult to cast. Usually turbine blade we would use some sort of investment casting technique to produce the blades, right? But in some set of turbine blade, especially in the combustion chamber, it had to withstand high temperature. So the material has to have high melting point. So we choose super alloy for that type of application. And because of the high melting point of the super alloy, it is difficult to cast. So it is easier to produce using powder metallurgy technique. Okay, so we will look at the advantages and disadvantages of powder metallurgy. Um, one of the advantages is it can produce near net shape and small size components like gears in hand watch, right? The like expensive hand watch that you can lend your friend, right? So like small gears, really delicate gears in the switch movement of the watch. It's got good surface finish. It wastes few material, so in fact you hardly waste any material at all compared to machining when you waste most of the material to produce like a small piece of the component. It can be fully automated and you can have high production rates of 500 to 1,000 parts per hour. That's quite good, quite high. It's good for metals with a high melting point, like tungsten filaments, hard to cast metals, not hard to cast, right? There's an R missing there. Hard to cast metals. Um, it can be used to manufacture a small and unique shape part, which cannot be produced by any other manufacturing process. Okay. It can be used to manufacture a certain part by mixing different metals, metals and non-metals, like cutting bits that I mentioned. When you are mixing tungsten carbide, which is a ceramic or a carbide, mixing it with cobalt powder, which is a metal, right? So you mix them together, you sinter it, you get your workpiece. Okay. Uh, to obtain this design properties, which is impossible with other working processes, right? So you can produce an exotic alloys when you use like powder of pure metals and put them together, and then you mix them together, and then you compact it, and then sinter it. Right? You can have exotic alloys, which might be difficult to produce in the melting form because some metals do not mix together when melt. Um, okay, you can produce component with uniform structure and without any defects. Okay, you have defect-free component and uniform structure, and you can have non-equilibrium composition as well. So because we are mixing powder of different elements together, we can have non-equilibrium composition. The disadvantages are the high costs. Okay, so the powder cost is quite high. The tooling cost is also quite high. So the powder cost is high because you have to produce powder by different techniques that cost a lot of money. Like for example, atomization, you have to heat up the metal, you have to melt it, then you have to atomize it using gas atomize or water atomize. But by melting it, you require a lot of energy, right? Um, so that will add to the cost of the powder. Okay, so high cost, but because you don't have any scraps, you don't have any waste, you will offset that high cost of material by the low amount of waste, right? So in some cases, if you are thinking about the finished workpiece, how much material is used and how much does it cost compared to machining process, you might need a bigger chunk of material before machine it into a small piece, and that big chunk also costs money, right? So you waste a lot of money. Okay, so the parts produced by powder metallurgy have low impact and fatigue strength as compared to other methods, right? So because you have a lot of porosity in there, even though after sintering you're getting rid of most of the porosities, but you can never get 100% dense like from other techniques. So because of those porosities, those are defect within your material, and it will give you some sort of uh, stress concentration point. So you get low impact property and low fatigue property. Health problem with atmospheric contamination of the workplace because you have a lot of powder. Uh, well, when you're working with a lot of powder, the powder might form into fume, and you might breathe in the fume, and that will damage your lung. So it is quite dangerous working with powder. Okay, so next topic that we're going to look at is 3D printing. All right, so in this case, we are talking about 3D printing of metal, right? So 3D printing of polymers is easy. It's been done, and you can buy a machine to use at home. It's not that expensive anymore, right? So you can think of 3D printing as an extension of 2D printing, like inkjet printer and laser printer that print into dimensional, right? But 3DP or 3D printing is the addition of raw material, usually one layer at a time, using a computer-aided design programming. It is also called additive additive manufacturing or AM, or sometimes fuse deposition modeling, right? So basically, you deposit each layer at a time and you fuse different layer together. So that's why it's called fuse deposition modeling. Okay, so what materials can be printed? Not only polymers, right, like I mentioned earlier, but also ceramics and metals. And it can be printed into different shapes. You can use metal powder and you can print into like this really complex steel parts, right? This is really complex, like intake manifold go to different like ports, etc. Um, impeller, rotor, etc. can be used to 3D print metals. Ceramics also can be 3D printed. There are 3D printed houses in China, in the US. There's some experiments doing that. In Thailand as well, um, if you are going in the Paramjet area, right? So there's an Amazon cafe just opposite the uh, King Mongkut University of Technology, Panakorn, just opposite that. That has been 3D printed, right? So you can see the wall is like sort of like this, right? You can see layers of concrete, right, in that Amazon cafe, that in opposite the Panakorn. Okay, so 3D printing can be used with polymers, ceramics, and also metals. So the advantages and disadvantages of 3D printing: you can have custom and unique parts can be made really cheap and really fast using 3D printing. You can have faster design changes compared with conventional manufacturing, right? So basically, you can design it and then you can print it out and see if it works. If it doesn't work, you can change the design, print another piece, and see if it works, right? Compared to conventional manufacturing like machining, etc., it might take longer time to machine a piece compared to 3D printing. You have less waste, especially for expensive material, right? So 3D printing uses powder uh, powder of metal to print, right? So it has the same advantages as powder metallurgy. Okay, so it also has a lot of the same disadvantages as powder metallurgy, like higher cost for larger volume production. The mechanical properties are not as good as other techniques, just like in powder metallurgy, right? The strength, endurance, uh, fatigue property, impact property are usually inferior to traditional manufacturing. You have fewer choices of raw material, color, and finishing. Right? For example, nowadays you can have a choice of pure gold, copper, titanium, niobium, uh, and alloys of aluminum, copper, cobalt, nickel, iron, titanium. So there are not a lot of choices that you can choose from. Example of common techniques used for 3D printing of metal. Right? So for polymers and ceramics, you can use a technique which is called extrusion printing. So you extrude, like you extrude the extrudates, right? The extruder will extrude the extrudates and print like in polymer, uh, or you can use like inkjet printing and print droplets. You get the same shapes, okay? But instead of like continuous line, you get like droplets that will fuse together to form the shape. SLS or selective laser sintering. So basically you have a powder bed. So you have just powder on the bed, and then you use laser you use a piece of laser, you shoot the beam down here, heats up the powder and fuse it together. So you get this shape of solid piece, right? The powder in other area doesn't get the energy from the laser, so it will stay powder. So when you remove all the powder, you get this piece here, right? And you can do that layer by layer. Projection stereolithography. This technique has been around for a while, but not for 3D printing, but it has been used to produce like microchips. Um, you might have heard like the chips is using 3 nanometer technology, 5 nanometer technology. The 3 nanometer or 5 nanometer that they are referring to is the wavelength of the light used for the stereolithography technique, right? So basically, you have a mask as the circuit of the chip that you want, and you have a photosensitive layer on top of your silicon chip. You're using the light shining onto the mask, onto this photosensitive layer. The area where the mask is covering the surface, the photosensitive layer won't be developed, right? And you can just sort of wash it off. So the area when the photosensitive material is exposed to the light, it will harden. So you get this shape. So you get so it uses the same concept. You have a photosensitive material, you have a mask, and you have a light source shining the light onto the mask, onto the material. Okay, and you get like you can do that layer by layer, so you get 3D printing. Okay, you can also have direct energy deposition or DED. In this case, it's the concept for this technique comes from welding, right? So you have a plasma welding, and also you have plasma. Well, you can have plasma, you can have electron beam, you can have laser beam, right? And you have a wire feeder, right? You can use electron beam, laser beam, or plasma beam to melt metal wire or powder. It's comparable to multi-pass welding technique, right? So basically, you can produce this shape quite easily, similar to welding, right? So and you can produce like three-dimensional um, part. Okay, so next technique is powder bed fusion or laser selective. The technique is using okay like like this selective laser sintering I mentioned earlier. So this is another name for it. It's called powder bed fusion. So basically, you have a powder bed, right? You have a powder bed. You have a roller and scraper to make the surface flat, and then like um, the laser will come down and print on the surface just like this. Just you can think of it as a 2D printing because it's printing just one layer, and then after this layer, the the build chamber will move down one step, and then more powder will be on top. More powder will be put on top, and then the roller and the scraper will make the surface flat, and then the laser will come down and print another layer. After printing that layer, the RAM will come down one step, more powder will be on top, etc. And you do this continuously, printing one layer, lower down the stage, more powder on top, printing another layer, etc. Until you get like large pieces like this. Okay, the laser selectively scans and melt powder metal on the surface, right? This technique can be slower as a roller is needed to spread a thin metal layer on top. After each layer is printed, All unmelt powder is collected and can be recycled again after treatment. So all these powder is not waste. You can reuse it. Um, okay. Application of 3DP in like automotive industry. Um, okay. So the 3D printing has been used commercially. An example would be the brake caliper in the Bugatti Chiron, right, has been 3D printed. The Bugatti Chiron is a $3 million supercar, right? So this is the brake caliper for the Bugatti Chiron or Chiron or Chiron. I've heard so many ways people pronounce it. Right? If it's strictly Italian, would be pronounced Chiron, but I've seen people pronounce it Chiron or Chiron or Chiron. Anyway, so this is the 3D printing rocket. You know, as well. Mm, okay. Wow, the animation doesn't work. Anyway, so I'll put up the animation in team for you guys. So they can be used in aerospace application. It can be because this is a video of a rocket being 3D printed. Unfortunately, the video doesn't work. It can be used in medical and biomedical application like 3D printing, uh, 3D printing the sternum and rib, like to replace the sternum and rib of a patient. The You can 3D print like false teeth, so you can basically do the 3D scanning, and you can manipulate the scanning in CAD program to be the shape that you want, and then you can print it using metal, so you can get like false teeth made from titanium in this case. Um, and you can use it to customize many dental products as well.